Hello, welcome to Quadratic Forms, or classifying. Well, welcome to Multivariable Calculus, or Physics. Um, Episode 60, and we are going to be talking about classifying the critical points of quadratic forms in more in depth. So, just a quick recap. Quadratic form. We're looking at quadratic forms like this: x squared plus bx y 2bx plus cy squared, something like this. And we said that, well, we can actually write this. This actually becomes this with in terms of the eigenvalues of let me just finish writing this down. This becomes this formula in terms of the eigenvalues of this matrix A. Right? So those are the eigenvalues of that matrix A. And now we're going to look at, and then we also said that the product of the eigenvalues times is equal to D, which is equal to f of x, x, f of y, y, minus f of x, y squared. So let's look at these a little bit more and we're gonna look at this general quadratic form here. We're gonna go more in depth into this guy. So starting with definitions, we want to say that, so if we have a matrix A, we say that it is positive, okay, positive semi-definite. I'm sorry, definite. That's an F, that's a D. When all eigenvalues are greater than 0, greater than or equal to 0, right? And then positive definite, so I'm just going to put positive definite when all eigenvalues are strictly greater than 0. And then 3, it's indefinite when there exists at least one lambda or one eigenvalue that has a different sign. Okay, does that make sense? So if and then obviously we have the same for negative. So we have negative semi ... negative definite. We have this. You have the exact same definitions for that. Okay. So this allows us to work with the following theorem. So here's our theorem. I might need a bit more space, but basically, we have, so if A is a CP, f of A is a minimum, local minimum, if A is positive semi-definite. Okay, so that's my notation here. So A is positive semi-definite. I'm actually just going to rewrite this as PSD, right? and then it has a max if A is negative semi-definite, and then a saddle point if A is indefinite. So if A is indefinite, right? And then otherwise, we don't know. And so if you recall, when I talked about the second derivative test, we had those rules, right? So we had f of x greater than 0, d 0, right? The minimum. F of x, or the second derivative of x, is less than 0 and d is greater than 0, right? And then here we have d is less than 0, and then here is d equals 0, right? These are equivalent definitions for the second derivative. So here we have, right? So that's, and then actually this is kind of a more kind of, I guess, a richer way of talking about this in terms of a property of the matrix that forms this quadratic form, right? So if you remember, I mentioned that, well, you could write d as a determinant. So this d is equal to the determinant f of x, f of y, fxy, fxy, or in this case fyx, right? That's that determinant here. And so this actually has a special name. This matrix has a special name, and it is called the, let me finish writing this. It is called the Hessian matrix, or Hessian, I think it's called, pronounced Hessian, but it's called the Hessian matrix. And so the Hessian is this, so it's f of x, x, f of x, y, f of y, y, f of y, 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 x, right? And in general, okay, the Hessian of a matrix, so the column of a specific, or a specific component of the Hessian, so labeled I, or labeled H, right, is equal to the ith derivative and the j. So the ith parameter is first derivative, and the second derivative is the partial derivative with respect to, I guess, j, if that makes sense. So a large matrix can look like, okay, the x, 1 squared f, then here is going to be x2, x1, and then so on. Here is going to be x2 squared, and then here we have x, this is x2, x1, this is the partial x2 squared, f, on and on and on and on. That's kind of what that h is going to look like. Right. So for a quadratic form, so for a general quadratic form, right, x t transpose a x, right, a is actually equal to 1/2 of the Hessian of a, or yeah, x is equal to exactly half of the Hessian of f. right? So that's exactly what that is saying. So that's why when we look at this 1/2, then this actually turns into, we're looking at the Hessian, and we're actually just taking these belong to these are eigenvalues of Hessian. Eigenvalues of Hessian, of the Hessian matrix, right? And okay, but now I can kind of hear you thinking like, okay, yeah, but these are just quadratic forms. Like these are just some types of functions. What about, not other functions like cosine y x or something like that, e to the power of y natural log x? So what about these weird functions, right? What about these? What do we do with these guys? Well, if you look closely actually at what the Hessian is so we have natural log of x, x2. If you kind of look at this, this should look a little, this structure of what this Hessian looks like should look a little familiar. I'm gonna finish writing this down. This is gonna be x3 x1 f, right? x3 x2 f. And that's because this is actually related to the gradient. So the Hessian is equal to the Jacobian. If you remember what the Jacobian was, that's the total derivative of the gradient of f. Right? So if you remember, the Jacobian acts on vector functions, and applying the gradient of f is a vector function. So take the Jacobian of the gradient of f and we get the Hessian. And that Hessian, we can use that Hessian for for optimizing, right? So I'm going to get into that next. So we're going to look at classifying critical points generally, and then we'll move on from there. And I think after that, we will be done. So we might have one more topic. And so see you then.